Hello. Thank y'all for having me here today. And so, as Blake mentioned here, I'll be talking about some smart irrigation technologies that can be implemented in the landscape. And the goal with implementing these technologies is, of course, going to be how do we achieve water conservation? So, just a little prelude here before I get into the heart of my talk here is just to review that, smart irrigation is when we talk about smart irrigation, what often comes to mind is just using different types of technologies. But technologies are simply just tools, okay? And so whenever it comes time to, maximize our conservation or try to achieve the best quality landscape when we implement these different technologies, we also have to make sure that we apply those properly with best management practices. There's no magic equipment when it comes to landscape irrigation that just installing it alone is going to meet all of our water needs in the future. And so keep that in mind that your smart irrigation, when we talk about these technologies, just tools, and they have to be properly implemented with using best practices to achieve the best water savings. So with that, let's start out with just a simple review of the state of irrigation technology. Okay, so when we look at in the bigger scheme of products, when we look at different types of technologies, we can generally break the industry or the products into two general categories of technology. We have what we call our irrigation control technologies and our irrigation application technologies. And so these pretty much do what they say. Control technologies help us manage when and how much irrigation occurs at a certain time, whereas application technology is going to be how we actually physically apply that water to the landscape. And so another way to look at this is we can compare our controllers to our applicators. So in general, when we look at the different types of control technology, we're talking about smart irrigation controllers. We actually have two basic subsets of smart controller technologies. Terminology keeps changing as time goes by in the industry. We generally refer to these as weather or ET-based irrigation controllers that take in climate data and use that information to adjust the irrigation schedule for your landscape. The alternative to weather-based or ET-based control systems is going to be our soil moisture-based irrigation controllers, where we have physical sensors installed throughout our landscape, and those sensors tell us when the soil has dried out to a set threshold, and then the controller can then turn on to refill the soil moisture. So two basic concepts there when it comes to controllers. But with technologies, we can add additional types of sensors to our controllers. And most commonly, what we see used in Texas is the use of rain shutoff sensors. And so with rain shutoff sensors, these attached to the controller, and they turn the controller off if it starts to rain while we're irrigating. That's basically what they do. They don't do a whole lot more than that. And when we get into more of the depth of this talk later on, I'll go into a lot more detail into their operation. We also have the ability to incorporate flow sensors separate from what you may have as a water meter on your property that we can use to track general water usage. But when we combine this flow sensors with our smart controllers, they can help us identify when do we have leaks or irregular flow occurring when our irrigation is operating. And then we can get alerts sent to us, or it'll turn off the controller and prevent excess water being wasted during those times. And then, of course, manufacturers are always looking at other technologies to incorporate with our controllers. When we look at application technologies, we can basically break application technologies into three subsets. We have drip irrigation, you have your irrigation sprinklers, and then more common today is the importance of pressure regulation. Drip irrigation technology really hasn't changed in the last 20, 30 years. Emitters still primarily work the same way they've always worked. However, we have seen improvements in the manufacturing process where we have much more durable drip irrigation products. So less chance of, it reduces the opportunity for those to be damaged. But also we have drip products that, because of their increased durability, can operate at higher than previously used pressures. And so with most with commercial drip irrigation products that we use now in professional landscape systems, we can operate these under very similar conditions to sprinklers without having to make too many additional adjustments to the design process or the installation. With irrigation sprinklers, obviously irrigation sprinklers are the most common method used to irrigate landscapes in Texas. We look at improvements in sprinkler technology, and that has come in different types of irrigation nozzles. Those include what we call high efficiency nozzles and multi-stream, multi-trajectory nozzles. And the goal of these new technologies is to produce more uniform water droplets so that we have a much higher application uniformity to our landscape. And that helps encourage that when that water leaves the sprinkler, more water goes into the soil where it can be accessed in the plant's root zone. We have less opportunity for water to directly evaporate in the air or potentially be blown away during windy conditions. And so that's what our goal is with these different nozzle technologies, to get more water from the nozzle into the ground. And then finally, pressure regulation. Pressure regulation has become a major issue in Texas. It's actually been a big topic for about 10 years now. And how do we make sure that our sprinklers operate at the correct pressure? And so I'll definitely be going into a lot more detail in terms of pressure regulation here later on in this presentation. So I've just gone through about 6 general categories of, or subsets of technologies. How can we identify what are the most efficient technologies out there for us to use? Well, one approach is to follow EPA WaterSense program labeling guidelines. And so if you're not familiar with EPA WaterSense, it's a program of the U.S. Environmental Protection Agency that's done in collaboration with industry to promote the use of water efficient products in the home. Okay. And so the goal of WaterSense is very similar to what we kind of saw with the Energy Star program, is to help consumers identify water efficient technologies. So just like when you go buy a refrigerator or maybe a clothes dryer, it has that yellow sticker that says this product will use this much power per year on average. That's kind of what the goal with WaterSense was, is to identify and label products that use 20% less water than conventional products in the landscape without sacrificing performance. And so the WaterSense program's been around for a very long time. If you remember from the late 90s, we had the launch of the WaterSense toilets. Everything had the little sticker on it here, like in the upper right picture. And then over time, WaterSense evolved to look at additional water features in the home, including bathroom faucets, urinals, showers, and different types of rinse valves used in commercial kitchens. But after a while, WaterSense started to look at, how can we save water outside the home? And so they started to address, irrigation products. Can these be WaterSense labeled with that little round sticker there for consumers to identify these products? And so, brief history here. EPA started labeling products in 2012. And the very first commercial landscape irrigation product that the WaterSense program put their label sticker on were on smart irrigation controllers that were weather or ET based. And so that came first. And then a few years later, then in 2017, they came out with the specification and started putting the label on spray sprinkler bodies. Then in 2021, they came up with a label for soil moisture-based irrigation controllers and their sensors. And then most recently, WaterSense released a notice of intent to come out with a label for in 2022 for sprinkler nozzles. However, in the February of this year, they have put a pause on that specification based on feedback from the industry. And so they're now taking a step back and reevaluating that specification because it covered a lot of different sprinklers in its scope. And so they're working with the industry to reassess that specification and move forward at a later time. So weather-based irrigation controllers, what does that mean in WaterSense terms? Okay. Well, for a controller to get that WaterSense sticker on it, it has to undergo a testing program where the controller is tested for 30 days for a standard landscape. And as a part of the labeling guidelines, it has to have a certain score. So it has to have at least 80% irrigation adequacy with no more than 10% irrigation excess applied during the test period, as well as there are minimum weather and rainfall requirements during that testing program. And a lot of these weather requirements are meant to make sure the controller is tested during a normal growing season. So you can't test it in the winter months. You test it during a warm season, and there has to have some rainfall occur during the testing program. And so, as I mentioned earlier, that program the label was released in 2012, and currently, and this is as of this past week, I looked at these numbers. WaterSense has labeled 448 different weather-based smart controllers. And so you may not have been aware that there are actually that many different types of controllers in the marketplace, but there's that many controllers, but it only comes from 21 different manufacturers. And so here's a list of the major manufacturers that have a product in their catalog that has the WaterSense label. And so pretty much every major manufacturer in the U.S. has a product in their catalog. And so just kind of go back and re-hit that 448 controller number. They base that based on model numbers. Okay. So for example, if I pick on Hunter, the manufacturer, as an example, if they have a 6-station controller and a 12-station controller that uses the same program to calculate the irrigation schedule, that actually counts as 2 different models. And so you can see here, as you know, you have different size controllers, different configurations. You can see where the number of model numbers would grow pretty quickly between these different manufacturers. Spray sprinkler bodies. Okay, so what about a spray sprinkler body has WaterSense looked at to identify those as a water efficient device? Okay, well, what they were looking at is sprinklers that had built-in pressure regulation in the sprinkler body. Okay, and so I already mentioned earlier there the importance of pressure regulation technologies, and I'm going to go into more detail of that soon. But when we look at pressure regulating sprinklers, we have these sprinklers that have the built-in regulators. So as pressure may fluctuate at your property, the performance of that sprinkler remains relatively constant. And so these sprinklers are tested under a wide range of pressures at a standard sprinkler nozzle to monitor the output pressure and the output flow rate to make sure that they regulate correctly. And so currently, there are over 625 sprinkler bodies that have the WaterSense label that come from 10 different manufacturers. And so you can see here in this little breakout diagram, there's an example of a sprinkler body that has that pressure regulator, this white component here built into the bottom of it. And so different models exist based on what the nozzle may require as far as operating pressure. You can buy these in a 30 psi, 40 psi, or 45 psi rating. And so currently you can see here are the 10 manufacturers. And then I've put in parentheses how many different models that manufacturer has. And so again, if I pick on Hunter as an example, they're a major manufacturer. They wouldn't mind me picking on them, I don't think. You can buy your sprinklers that pop up different heights. So if you have a sprinkler that pops up 2 inches, 4 inches, 6 inches, those all count as different models. And so you can, again, see how the number of models would increase based on different model numbers listed with the same type of regulator installed inside of them. And then one of the more recent products to get the label, and this was no easy feat for Watersons. It actually took over 5 years for them to come up with a specification to label soil moisture-based irrigation controllers. And so the use of soil moisture sensors in conjunction with your irrigation controller to determine if and when irrigation is needed. And so testing program about this is pretty simple. They put these sensors in a standard soil and they test them at different moisture contents, a wet condition, a dry condition, and then a condition in between. And they verify that the controller and the sensor can recognize there's 3 different moisture contents at those different conditions. And then the user would then set their own defined threshold of how wet or dry do they want the soil to get between irrigations. Now, we actually have lots of manufacturers of soil moisture-based irrigation controllers. However, at this time, only 2 manufacturers have submitted their products for testing and received the WaterSense label. And those 2 major manufacturers are Baseline and Aerometer. And so I have here examples of both those sensors. On the left side here, we have the Baseline sensors. These come in different models as well. These longer sensors are meant to be used directly with a Baseline irrigation controller. However, they also sell these add-on devices, like you see down here, this WaterTech module here. And with this WaterTech module here, we can actually add that to any other manufacturer's irrigation controller. So that becomes an add-on device that if you have another brand controller, you can add this box to your controller, and it allows you to incorporate a sensor to then use that soil moisture sensor with your existing controller. And that works the same way here with the Aerometer-based controller, this green controller. You can see very different styles of technology. The Baseline is a very digital-based, whereas Aerometer is more analog-based here, where we have a simple dial here that you read the installation guide, and based on your soil type, you can set what value they recommend you using. And again, this box connects to any manufacturer's controller to determine, okay, on the days you need to irrigate, is there plenty of moisture in the soil? And if there's plenty of moisture, then the controller won't turn on the zone. But if the landscape is dry and the sensor tells the controller the landscape's dry, then it allows the controller to turn on for its preset amount of time. And I'll just point out here, because if you pay attention to different products in the industry, the sensor used by the Aerometer controller is the same sensor that's used by the Hunter brand soil moisture model, but the Hunter box has not been labeled for WaterSense at this time. But they're the exact same sensor technologies, same sensors, just different interface boxes are used. But I'm told that Hunter may be getting their label pretty soon, so that's why I mentioned that as well. Okay, so that's a brief overview of some background on some different technologies. And so WaterSense is a great resource. They've done a lot of the initial legwork in filtering through the products in the industry to see what products can be tested and proven performance. But we've been doing our own testing program here at our laboratory in College Station since 2009 of different irrigation products. And we've worked with EPA on the development of their testing program, but we've done something separately, kind of like an end user consumer study type approach to products that we see most commonly marketed and installed here in Texas. And so I'm going to go through a brief overview. It may seem a bit technical, but I'll try to keep it as simple as possible. Some of our test results from different products and how you can take that test data to be more practical use and get applied results in potentially your own landscape. And so we've been testing three biggest programs have been rain sensors, sprinkler bodies, and irrigation controllers. So rain sensors, in Texas, state regulations require all irrigation controllers that were installed after 2009 to have a rain or soil moisture shutoff device installed on the irrigation controller. This is also a part of most city regulations as well for new irrigation systems. And so we see rain sensors being the most commonly used sensor used with controllers because they typically are the least expensive option when it comes to adding a sensor to a controller. Sensors vary from $20 to $50 depending on is it just rain only, or is it measuring temperature as well? Is it a wired model, or is it a wireless model? And there's lots of different manufacturers and models of rain sensors out there, but there isn't a whole lot of understanding about how these work and how much water they save. And so we've been looking at this in our program for a while. And so here's just an example of different models. These are probably the most commonly we see here used in Texas. You could buy these at any irrigation store or even places like Home Depot or Lowe's. Okay, so these aren't hard to find. Okay, so we have different models here that we tested. And during our initial testing period, when we got our original funding, we tested these controllers for 2.5 years. And it was a great period to test rain sensors, actually, from in 2018 through early 2021. Here in our laboratory in College Station, we recorded 97 rainfall events and 82 inches of rainfall during that 2-year period. So great time to do a rain sensor study. You did not have a major drought during that period. And so all these sensors were hooked up to a data logger computer, and we recorded when they triggered and resumed irrigation throughout the year. And so here I have a little snippet of data from the initial year. And what we can see here is each little color bar represents a different model of a rain sensor. The blue line is how much rain occurred on a particular storm event. And then how many hours did the rain sensor turn off irrigation for? And so we can see that, there's a lot of consistency among the manufacturers here. They were all installed real close to each other. So we expected very similar performance. No one brand really stood out in the first couple of years as having a significant advantage over the others. They're all relatively pretty close within a short period of time. But what we can see here is that the amount of time these controllers triggered for vary quite a bit. And so if I draw this line here, and so how many times during that period did the sensor say no irrigation was needed for more than 48 hours? Okay, well, we can see we only have 6 major rainfall events really during this period where the controller turned off for over 48 hours, so 2 days. The majority of the year when it rained, it was 24 to 48 hours was the common off time. And so that brings up some concerns, because if you get an inch of rain on any given day, and that's not unreasonable and especially with recent weather. You shouldn't have to irrigate for at least a week. That's, a 1 inch irrigation, 1 inch of rainfall is plenty to meet the water needs of a plant for at least a 7-day period. And so we don't want to see controllers turning on too soon after a rainfall event when it's not necessarily needed. And so you can just see here that, most often what we found was that about 24 hours seemed to be the norm when it came to how long the sensor is turned off the controller for. So we looked at what affected how long the sensor turned off the irrigation. And so 2 basic analysis we did was we looked at how much rain occurred versus how long did it rain for actually. And we found some very interesting results. And so I'm not going to go into a statistics class here, but we have a simple scatter graph here from all the sensors here. And so this graph tells us here at the bottom how much rainfall occurred on any given storm event and how many hours did the sensor trigger for. And so there's really not a big pattern here. When we try to do some analysis here, we can see there's really not a very good correlation in these dots, except for you get down here to the very bottom left corner. So it's kind of random, you can see here. But if we go and we look at the second analysis we did, okay, well, if we don't look at how much did it rain, but how long did it rain for, we found something very interesting, and that has a stronger correlation to how these rain sensors perform. And so while not perfect analysis here, we can see there's definitely a trend forming in the data to where the longer it rains, then obviously the longer the sensor triggers for, regardless of the amount of rain that actually occurred. And so in our earlier analysis, we found that the length of the rainfall event is really what had the greatest impact on how long the sensor triggered for and how long it avoided the controller from turning on irrigation again. So why were we doing a lot of this analysis of rain sensors? Well, one question that we often got was, okay, when I program my controller, should I take into account the effects of rainfall in my runtime, or should I always assume worst case conditions when I program the runtimes in my irrigation controller? And so that's what we were trying to get data to better answer that question. And so as the second part of this testing program, we went to a real neighborhood. And so here in South College Station, we found some volunteer homeowners that were all within 2 streets of each other. Some of these were backdoor neighbors, so real close to each other. And we evaluated their irrigation controller programming, how often they irrigated, and we compared that to the operation of their controller given any individual rainfall event that occurred during a period. Now, what's unique about College Station is we don't have water restrictions. We're one of the last few places in the state where you can water any time or any day of the week that you wish. Anytime, there's no time of day in the mornings. In most cases, there's just guidelines that give you recommendations not to irrigate at certain times. And so you can see here from this subset of 7 homeowners here, or 8 homeowners, I'm sorry. Some homeowners irrigated 3 days a week, some irrigated 2 days a week, and there was one homeowner that only irrigated 1 day a week. And they all had different start times, most of them irrigating in the early morning hours. And so when we looked at their schedules and when they irrigated versus when it rained, we could go back and see, okay, how often did the controller actually turn off how often did the rain sensor turn off the controller to where it did not irrigate at a scheduled event? Okay. And sometimes this is just kind of bad luck. You can see here, like, for example, when it says when it's blue, that's a rain day. And did it need to irrigate that day? Yes or no? Well, if it rains at 2 a.m., but the controller doesn't irrigate till 5 a.m., well, then that rain event was probably going to be canceled. But if the controller turns on at 5 a.m., but it doesn't rain till 1 p.m., well, the irrigation has already occurred for that day. And so the controller didn't know it was going to rain, and it irrigated in advance of that event. And so we looked at that breakdown, and we can see here a lot of these weeks here had pretty big rainfall events. And so most of the weeks we analyzed were when we had over an inch or more of rain occur. And so when we looked at that analysis, how many total irrigations could have occurred if there had been no rain, and then how many times did the sensor prevent irrigation, we found that it only prevented about 25% of the irrigation events. So, not a huge savings, but 25% is a 25% water savings. And a lot of this did come down to, the luck of it. Did you irrigate on Monday, but it rained on Tuesday, and then vice versa? And so we had this nice subset of unique schedules that homeowners were implementing on their own to evaluate the potential. And we can see here, there is potential to where you could save upwards of 45% if your schedule just aligned perfectly with the normal rainfall pattern or the rainfall pattern during that season. In other cases, the sensor didn't produce very much savings at all. But I think we're comfortable saying, on average, 25% savings just by having a rain sensor on the controller. Okay, well, let's look at pressure regulation in sprinkler bodies. Okay, so here's a little picture of our testing program in our laboratory where we test sprinklers. And why is this important? Okay, well, sprinklers have to have pressure to pop up and distribute their water. Okay, however, based on the size of the sprinkler, the pressure requirement can vary based on the manufacturer's recommendation. The further you want that sprinkler to throw water, the more pressure you need. Shorter distances require less pressure. Now, utilities like to have high pressure. They have to keep so much pressure in the utility network to keep water moving. And at the end, homeowners like yourself, you want to have plenty of pressure when you go home and you turn on the faucet or go take a shower. You want to have plenty of water come out of those fixtures. You don't want to just see it slowly dribbling out. But most sprinklers don't require significant amounts of pressure, whereas most homes, depending on your location, generally have 60 to 80 psi at their water meter at the end of the street or at the curb, whereas sprinklers only require on average 30 to 40 psi, those that are used in residential settings. So we can see here there's a big gap here where you have almost twice the amount of pressure you need being delivered than what the sprinkler requires. And when we deliver too much pressure to our sprinklers, we get poor performance. Okay, here's an example of a landscape here in a subdivision, actually in Bryan here, operating at high pressure. And what's the result of that? We have this very fine misting of water occurring, and that's producing very fine water droplets that are going to evaporate. They're going to blow away, and that water is not going to be applied uniformly to the landscape. So you could potentially have dry spots between your sprinklers because the water's not being thrown uniformly. So how can we overcome that? Well, we would use pressure regulation. Okay, so when we compare a conventional sprinkler to a pressure regulated sprinkler, what does that mean? Okay, so here I have some simple data here. We have this blue and gold line here, our conventional sprinklers, that as we increase the amount of pressure going into that sprinkler, then the output pressure increases as well. Oh, excuse me. So what goes in comes out. Okay. The sprinkler does not control anything. It just does what it does based on what it receives. But with a regulated sprinkler body, the idea is that as the pressure increases going into that body, the regulator inside of there manages that pressure by burning off the excess pressure with a regulator and keeping the output performance minimal, or decreasing the performance so that it doesn't put out extra pressure coming out the discharge side of that sprinkler. So with a regulated body, the input pressure is always going to be greater than the output pressure. And we can see that here in this graph here that, for example, as we went from 30 to 70 PSI in testing, the one manufacturer got no more than 35 PSI from when we started at 30 PSI versus a conventional sprinkler. As we increase from 30 to 70, the pressure truly does increase from 30 to 70. So why do we concern ourselves about this pressure? Well, as pressure increases, so does the flow rate. You're pushing more water through that sprinkler. And so we can observe that as you put too much pressure through that nozzle, you're going to increase your water usage. And we can see here, based on some of this data, that going from a base flow rate, so if a sprinkler was rated, for example, for in this graph here, 1.5 gallons per minute at 30 PSI, but we operate that sprinkler at 70 PSI, well, without pressure regulation, that sprinkler is going to use an additional 0.9 gallons per minute. And so if your zone has 10 extra sprinklers on it, then you could be using 10 more gallons per minute for each minute of operation, just because you're operating at a higher pressure. So by making sure we maintain the nominal pressure that the manufacturer recommends, we're reducing our water usage and saving water in the long term. And we've verified this in the lab as well as in field studies. Here's an example where we did a audit retrofit at a apartment complex in College Station. So this is the irrigation system before, and the system does exhibit signs of high pressure. We can see that misting occurring at the sprinkler heads. Well, we tested the system, and then we replaced those sprinkler heads with sprinkler heads that have built-in pressure regulation using the same nozzle. And we can see that when we turn that system back on again, we get much cleaner streams of water coming out of those sprinklers. We can observe that between the two photos. But what does the data show? Okay, so beforehand, we were seeing pressures in excess of 55, 65 PSI at the site. And so the data shows us that, okay, how much water was being applied? Surprisingly, the rate at which water being applied remained relatively constant. Somewhere between 0.23 to 0.25 inches per hour, which is what that manufacturer actually rates that device for. So the precip rate was relatively unchanged, but we did observe a 27% increase in the uniformity of application. Okay, so even though we're still measuring the same amount of water being applied, we're applying it much more uniformly over that area. On top of that, because now that we're regulating it, we're actually reducing our water usage. And so we were able to save over 2 gallons per minute during the operation of that system by incorporating pressure regulation, which was a 23% reduction in flow. And so we combine all these concepts together, the decrease in water use and the increase in uniformity, that overall increases efficiency. And so that's what we always want to do, is how can we incorporate the technologies to increase the efficiency of our system? We're using our water more wisely. Okay, and then where do controllers fit into this? Okay, where do controllers? Well, as I mentioned, we've been testing controllers since 2009 in our laboratory, and our lab has evolved with controllers over the years. When we first started this testing program, most of the manufacturers' smart controllers had a weather sensor attached to them that measured the climate conditions there at the property and then fed that back to the controller to make its decisions on how much and when to irrigate. And that's what we see over here on this right photo here. There we see the outdoor controllers, and they all have their mini weather stations attached to them that they're collecting data and calculating irrigation schedules. But in the last 8 to 10 years, really since about 2012, 2013, when we first saw the first Wi-Fi based model come out. Now everything seems to be internet based. We now have a separate testing program just for what we call the Wi-Fi based irrigation controllers. And so these are the ones that connect to your home network, and they're tied into an online weather resource to collect real-time data to then calculate irrigation requirements. Okay, so both programs are running side by side. Just one's in the laboratory using Wi-Fi and internet data, one's outside using its own sensors. And just for reference, we evaluate these under a range of conditions. So how would this controller perform if we were irrigating flowers, turf grass, ground cover, different types of shrubs? So we program these controllers for a wide variety of landscape conditions. But one of the challenges we have with our model of smart controllers is in programming. Okay, and every controller has a different programming setup. Some controllers ask you a lot of details about your landscape so that it can do all the calculations for you, which is great. But about half the controllers ask you to enter in a base runtime and frequency, and then the controller just manipulates that. And so in those cases, it can be very challenging because if you start with a poorly executed initial runtime and frequency, then the controller is going to be just working off of that. And so initial setup is very important to consider, making sure the controller is properly programmed. Some make that much easier than others. And so you can see here, how many controllers did we have to enter in a runtime for, or did we not have to enter a runtime for? So we calculated a base schedule based on the best science we have available and implemented that as practical as we could based on the setup of those different controllers. So all of these controllers were set up as similar as possible that we could. So I'll give you an overview of last year's data. Okay, this runs continuously. It's running right now, but let's look at last year's performance data. And so here what I have are some slides that show you the runtime philosophy of different technologies. And so I've highlighted a flower zone, a turf grass zone, and a shrub zone. And so here we can see with the Rainbird irrigation controller, how did it schedule irrigation? Well, it had shorter run times in the spring, in March, and then the run times increased into the peak of August, and then the run times decreased. So we can see here, this controller is making seasonal adjustments. Ideally, it's making weekly adjustments to how much it applies to these three different plant materials. We compare that to a Hunter HydroWise controller, and this was a controller that we entered in a runtime for, and the controller never changed the runtime. All it did was adjust the frequency. Okay, so it decided, did it need to irrigate or did it not need to irrigate using the runtime that we already gave it? And so we can often see big gaps in the runtimes. And generally, we can go back and look at the weather data and see that, okay, where we have these gaps, there was rainfall that occurred. So the controller was turning off the zones. It was not allowing any irrigation to occur during those periods of rainfall. And it was given the landscape sufficient time to utilize that rain that occurred before it decided that it needed to irrigate again. So we see that trend occurring here with this manufacturer. We look at Rachio here. Rachio is kind of a mix of approaches, I guess you would say here. In the spring, it had long run times, but did not irrigate very often. And then in the summer months, it had short run times, but it irrigated more frequently. Okay, so it kind of had a combination of approaches occurring here, but it did change the run times and it did change the frequency on its own. Here we have the rain machine, very similar to what we saw with the Rainbird. We have this curve approach where the runtime increases into the peak of the summer in August and then decreases down. Okay, so that controller is making runtime adjustments. Excuse me. Here we have the Beehive controller, very similar scheduling approach to what we saw with the Hunter. Had the fixed runtime for the most part, and it just adjusted its frequency. Here we have a Toro controller, again, very similar concept. But if you notice in the last few controllers there, there's not a whole lot of irrigation occurring in that zone 6, which was our shrub zone. And so why was that? We looked at ourselves. And what's interesting about the 2024 analysis is based on our scheduling model we used, we showed that the soil never technically dried out during that period from March through December. We can see here at the very beginning that, a full moisture profile was around 1.7 inches. And so we had lots of rain in March, April, May, June, early July. And so that kept the soil moisture pretty high. And then we got into this dry period with a little bit of rain in August, early September, where the soil was drying up pretty quick. But right before it dried out, it got some more rain. And so we can see why the controllers were performing the way they were, because we had lots of rain. The soil never really dried out. So there wasn't a need to irrigate on a weekly basis. 2 irrigations over the 6-month period was actually very sufficient for what that plant required. Here's another example of a controller's approach with the Hunter Solar Sync model. Again, we see this one actually did multiple run times per week. And so, one day of the week it may have had a long run time, another day of the week it may have had a shorter run time, but the trend still continued where it increased into the summer and then decreased into the fall. So that's how they performed. But what does that mean in terms of their water conservation potential? Okay. And so I'm going to just highlight some detailed performance here, not to get into a lot of detail here, but here we can see that here's the performance of the controllers in the spring. How many inches did they apply for each of the 6 landscape zones? And so if we're looking at just this graph at a glance, the dotted line is what I would say would be the optimal performance. That's our soil daily balance that we're calculating in our irrigation model. The solid black line is the weekly water balance model of the Texas ET network. And so the dotted model is, I think, a little bit better, but anything that performs between the 2 lines, we could probably consider to be fairly adequate irrigation. But if they're above these 2 lines, they're applying way too much irrigation. And so we can see some controllers are having a tendency to put out excessive amounts of water. And when we quantify that, we can kind of look at these numbers here and see that. And so I don't expect you to look at these numbers in too much detail here. But what I've done is I've simplified this a step, and I've highlighted the values that are within 20% of our calculations. And so if they're in yellow, that means they're doing a pretty good job. And so I'll just point out, we can see that in the spring, these 91 days, we did our analysis that the ratio, 5 of the 6 stations were within 20% of our calculations. The Hunter HydroWise had 4 stations, and then the Beehive and the Solar Sync had 3 stations. Some controllers were not within 20% of our calculation at all. So that's a bit concerning. But what's more interesting is when we move into the summer months, we see a different trend occur. We didn't get a whole lot of rainfall last summer, and so the 2 models are much closer together. And we come back and we look at the actual values with those graphs there, and we can see a shift. In the spring, ratio had 5 out of the 6 that were within 20%. Well, now they only got 1 station. Now the HydroWise has 5 out of 6. Rain Machine had 2. Beehive had 2. Toro had 2. Rainbird and Toro only had Rainbird and Solar Sync only had 1 station within 20%. So we see a shift here that as the seasons changed, the pattern did not continue. And then finally in the fall was very, very dry. And we can see here the 2 models are almost on top of each other. So we have lots of confidence in the calculations when the two models come into agreement here. And so you can see here during this 56-day period in the fall, there was only 1.2 inches of rainfall recorded. And now we saw that the controllers that did poor in the summer did very well in the fall. And we see multiple controllers have 4 or 5 zones within 20% of our calculations. So we have this back and forth occurring between the different manufacturers. And so I've ranked them here. So which controller did the best in the spring? In the spring, it was the Beehive. But in the summer month, it was the Hunter Solar Sync controller. But then the best controller in the fall was the Rainbird controller. And so we see this wide range of performance as the seasons change, that no controller was consistent across the 3 seasons for the most part. So you kind of average out those rankings. Obviously, nobody was 1-1-1 to take the lead to say that that was the number 1 controller. But we can see that, there's a top 3 controllers, that averaged out with similar performance. But 2024 was just 1 year. We compare that to the last 4 years. And again, we see lots of inconsistencies. What did very well in 2021 may not have performed well in 2022 versus 2023 versus 2024. And so we're starting to see some trends, though. And of course, the controllers are running right now. And so we're on the verge of having a complete, we're in the middle of our 2025 data. And so we're learning more about these controllers to see, which ones do we recommend. We don't quite have one that we fully endorse yet, but we see controllers that have a much more consistent performance and as far as how much they irrigated versus what we calculated was needed. So you can look at this list and see, okay, maybe which ones do I want to avoid? Or you go back and look at the previous list and say, okay, am I mainly concerned about the summer months? Which controller did the best in the summer? If you're more concerned about all 3 seasons combined, then you kind of look at the overall average. So we look at the controller summary. Nobody had perfect performance in the last 10 years of looking at controllers. We've never had a controller have a perfect performance. But what we do see are positive things. This is technology. It's always improving. And so we can see, we've demonstrated that the controllers do make adjustments. So the controllers do respond to rainfall. They either don't irrigate or reduce their run times. And so we look at those first 2 bullet points there. You will save water with most of these controllers compared to a conventional clock where you just set it and never touch your run times again, and you just let the controller run on that fixed schedule over and over and over again. So by letting the controller have some management ability to override and make its own decisions, you can save water. And the amount of savings does vary based on the season, the year, and the type of the landscape we've seen. But what we really like is that, with these internet-based Wi-Fi controllers is, it gives you an extra level of flexibility in managing that irrigation system, because now you can always just pull out your phone, click on your controller app and say, you know what, my lawn looks really good right now. And we just got through having 2 weeks of heavy rainfall. I'm just gonna turn my controller off for a while until I think, things change. And so it gives you that extra step versus having to go out in the garage. And, back when I had my own irrigation company and I go to someone's house, you go in the garage, say, where's the controller? I have to move, a stack of Christmas boxes or a shelf or something to access the controller itself. Well, now you don't have to worry about that. The controller is in the palm of your hand. And so you can make better decisions on your own as far as when you irrigate and when you don't irrigate. So all of these technologies are just tools, okay? And so there's no magic single-use technology that we can implement to get all this in one. It's a combination of factors. So, using pressure regulation so that we have more efficient application of our water and our sprinklers, along with the good control technologies, either using Wi-Fi technology or making sure we have our rain sensor properly working. And when we combine all that together, we can achieve very good water savings. Now, just because you implement the technology does not always mean you'll get the best performance. You have to start with a well-designed and installed irrigation system. It's hard for these technologies to fix poor designs and poor installation. So you have to make sure you're starting with a good installation. And a way we can do that is making sure that we're always using a licensed irrigator and they're following the state irrigation regulations for design. And if we follow those state regulations for design, we should have a good quality irrigation system to manage. And then when we look at this all together, a beautiful, healthy lawn can generally be managed with less water.